I would like to introduce Marco Slaviero. He's from SensePost, a South African company dealing with computer security and almost very well known for a lot of tools they published. Tools some people that I already noticed in the audience use or have used. And Marco will talk about Memcache and applications that are using Memcache and what you can get out of this stuff. And I think it's a very, very interesting and actual topic. It's especially because these kind of concepts are very, very commonly used with internet-facing systems, I think.
Yep.
Okay, so Marco, let's start.
Thank you very much. So before I actually get started, I just want to touch on one thing that Enno mentioned in his keynote, and that's this notion of Komodo. So if you subscribe to Daily Dave, you would have seen Dan Gear's mail I think 2 days ago. But basically what he points out with Komodo is the fix is not to use revocation lists or OCSP. The fix that we've been told is appropriate is to hard code the serial numbers of the bad certificates inside the browser. Consider that. It means that CRL's OCSP is completely, it's not relied upon by the browser manufacturers. So I'll just leave you with that in terms of broken internet. But on to my talk, which is this thing called cache and delivery. I want to thank ERNW for inviting me over to present this. This came out of some work that we did last year and was presented in a preliminary form at Black Hat, and then we worked a little more on it. I'm from South Africa. Just to put it in context, if we're known for anything, it seems at this point, it's the vuvuzela, that loud droning instrument that you would have heard at the World Cup. Contrary to popular belief, it's not a cultural instrument. It's sort of 10 years old. It's not actually that important. But there are a lot of fun to play if you're inside a stadium with 80,000 people or so. Anyway, so well, I guess just a little bit of background. Michael already mentioned I'm from SensePost. SensePost has been doing sort of security stuff for quite a while. Mostly we focus on penetration testing, application testing as well. But we've been around for a bit, and occasionally we get invited to these kind of conferences. So last year, to put this into context, or this particular talk into context, well, actually in 2009, sorry, time flies, we did a talk called Clobbering the Cloud, which specifically looked at cloud systems and how we could find relatively basic vulnerabilities in them, but vulnerabilities that got us quite far. And specifically, we looked at Amazon, we looked at Apple, and we looked at Salesforce.com. And we found what we thought were some quite interesting, really architectural flaws, process flaws, rather than technical vulnerabilities. And in a similar line, and it touches on, again, what Enno was saying in his keynote, is that we are dealing with a lot of change in the way that we trust systems. Essentially, we're offloading that trust. Well, we have to trust these systems we don't necessarily understand. And so with our Clobbering the Cloud talk, we looked specifically at the front end. So what it means when you use Amazon as a user, and MobileMe and Salesforce and so on. And so what we then decided was to look behind the curtain to see, well, these guys rely on software as well. They're just users of software, and in some cases, vendors of software. And it made sense to see, what are their systems looking like? As Enno said, ask them the question about the systems that they use. I think it was, there's one of the US presidents, which I won't mention names, he had this phrase which said, trust, but verify. So you can trust someone, but you can only trust someone as far as you can ask questions about their controls in place. And so this year, we're going to look behind the curtain. Now, this is a point that I'm going to, well, there's a couple of changes that we see in this thing called cloud, and I'm not going to define cloud. It's pretty fuzzy as it is, at least in the pictures. So I'm not going to get into a discussion of what it actually means, but I think the things that interest me when looking at cloud systems are that they generally involve massive data sets or large user populations. Not always, but the really interesting applications certainly do. And that gets interesting specifically for Memcached. There's also, when it comes to offloading of these services, a lowering of the barrier to entry. They become less complex to use. And we see that not just with cloud systems, obviously that's that's computer systems over time. They generally become less complex to use. But what it means is that as they become less complex to use, you have a greater influx of people who are using them, and those people have less and less or fewer and fewer skills. So we see this lowered barrier. And what comes out of that is people are less reliant on experts or people who know what they're doing. And it also means specifically when it comes to developing applications on, say, EC2, you see things like developers moonlighting as admins or developers moonlighting as operational people. Because it's easy, they can log into a website, click run this image, and now they've got a full LAMP stack, and they can start deving and they also manage it. And it's great because you save on the cost of a network administrator. I'm going to come back and touch on this right at the end. But I think this is a pretty fundamental shift, and I think it can be quite a dangerous one. So looking at these scalable systems that we're interested in, this is just kind of like I guess, the broad background slide that you sort of start broad focus in. But when it comes to these scalable systems, the idea is always to make it cheap to scale. So you don't want to be reliant on really expensive hardware, really expensive architectures. You want to be able to multiply very easily when you scale. So you scale horizontally using cheap hardware, commodity hardware, and free or close to free software. And that allows you to distribute your processing amongst all of these nodes in the network. But what that means is that it becomes a really network-centric architecture, right? The network's very important. Without the network, you don't get the benefits of the scaling, and you don't get these massive systems. And when it becomes this reliant on the network, what we tend to find is homogeneity within the systems in the network. So they all look the same. It's easier to manage when everything looks the same. So you scale one system many times. You don't have 5 different systems that you rely on, or 5 different versions of a piece of software. You have one piece of software, you scale it across all your nodes. And so we kind of get into, when it comes to these very large systems, eventually you bump into the need for caching. And sort of this image just demonstrates what happens when you can only serve one request at a time. Things kind of back up, right? So serving requests in scalable systems becomes really, really important. And you need to be able to serve those requests as fast as possible. And in many, in most systems, I guess it's a kind of a truism, but just go with me here. What you'll find is that data tends to remain constant. So the number of times that data is written to is far lower than the number of times it's read. That model is, it's not universally true, but it's true for many kinds of websites that are large and scalable. And you can pick your examples there. So your average Wikipedia page is going to be browsed many more times than it's written to. If your Facebook profile is written to more often than it's read, then you probably need to get a few more friends. That would be my professional opinion. YouTube video links, ads as well. And so each of these pages is written a few times but read hopefully many times. But in any system, generating the page is can be quite an expensive process, especially if there's database interaction involved. There's multiple systems where we have to pull in adverts or at least compute user preferences, decide what's going to be shown on this page based on the user's profile. And so there could even be multiple database queries that any given page is reliant upon. But if the contents of that page are not changing, then every time you make a database query, it's a little bit wasted, right? And so ideally, we want to cache that. And so store it in a way that is faster than having to go to the database directly and have a parser figure out a SQL statement and then actually get the info and then pass the results and so on, which is all quite messy. So when it comes to caching, sort of the mantra then becomes don't regenerate, rather regurgitate with sites. And so looking for caching solutions, there's a whole bunch of them that are available. This problem is well known. This is not a new thing. Caching has been going on since the early days of computer science. And so if you're trying to build specifically scalable web applications today, you've got a whole bunch of options to choose from. They're not all identical. They've got different features, but you do have a number of options out there. And because there are so many options and our talk was somewhat limited, we had to only pick one, and we went with Memcached. Memcached is probably the most popular caching software, and it's used in a number of pretty high-profile websites. So you'll see there's all the logos there. So Facebook specifically have got a custom implementation of Memcache that they run internally, or at least that's what the interwebs say. So a little bit about it. It was written in 2003 by a guy called Brad Fitzpatrick, specifically for LiveJournal. LiveJournal, as a blogging platform, encountered exactly that problem. Every time they needed to generate a page, it became really expensive. The servers were taking a hit. So one of their engineers said, no, forget that. He can do better. And he put together this piece of software called Memcached. It's quite a small piece of software. So it's only about 10,000 lines of code. It's also relatively platform independent. And to break it down, it's non-persistent network-based key-value store. Now, it's quite a mouthful. We'll just look at each of those. So the first one is it's non-persistent. The whole cache lives in memory, right? It never touches disk. It means it's fast to interact with, to read and write from, because disk activity doesn't have to happen. That's great. The second one is it's network-based. So this cache sits somewhere else on the network. It can sit on the same machine as your web server, but typically you'll have it sitting on a dedicated machine with lots of memory that's not having to do other work. So it sits somewhere else in the network. And then the last one is it's a key value store. So if you're familiar with a Python dictionary or a Perl associative array, that's all this cache provides you with. You provide the cache when you write into it. You say, this is the name of the thing that I want to write, essentially a variable name. And you say, this is the value that must be associated with that key. All right? So you have a key and a value. And when you come back at a later time to retrieve the value, you simply say, give me the value of this key, and the cache will send it back to you. All right, so pretty basic functionality. Current version for Memcache is 1.4.5. It's actually been like that since at least towards the beginning of last year, which is interesting given some of the bugs in the software. Anyway, let's look at the internals. This is the architecture of a basic Memcache installation. Now, it's a bit messy, and it's a multi-tier architecture. But the important thing is that with all of those, the load balancer, web servers, app servers, and databases, Memcache sits here off to the side. It's not in line. So if your Memcache dies, then your application will still be served. It just happens at a much slower pace if the cache is working correctly. All right, so that's sort of where it fits in architecturally. I mentioned that this was an in-memory cache only. So the data that you store within the cache never actually touches disk. And so what happens is when Memcache starts up, and the reason I'm getting into this details is because the intricacies of actually how it stores are sort of important for mining. But when Memcache starts up, it reserves a whole bunch of memory for itself. Obviously, it doesn't want to have to allocate every time a new request comes in. So it performs its own memory management to a large degree. And it takes the memory that it gets and it divides them up into equal size chunks. And these chunks are called slabs. And the slabs are the things that we're interested in. So for example, a slab may be 1 meg in size. So at boot up, it reserves a gig of memory, and it breaks that up into 1 meg chunks. And then each of those 1 meg chunks is a bucket, and that bucket is responsible for holding data that fits within a certain range. So for example, a particular bucket may hold data that lies between 100 and 150 bytes. Right? And the next bucket would then hold data that lies from 150 bytes to maybe 250 bytes. And the size of the data stored within a bucket varies depending on the bucket. But the bucket size remains constant. They're all, for example, 1 meg big. So what that means is that if there is a bucket that stores data up to 1 meg in size, because that slab is only 1 meg, that bucket's only 1 meg, it only can store 1 item. Conversely, if the data that is being stored is 10 bytes big, then you get a meg divided by 10 bytes. That many items can be stored. Okay, again, it's kind of roundabout, but the slabs are important. The way that Memcache evicts stuff from the cache, so it uses a least recently used eviction strategy, but it's also lazy eviction. So it's not checking every couple of nanoseconds to see if anything needs to be removed from the cache. When you try to get a key, it will check the expiry time at that point, and if that key's expired, you just won't get it back. Okay, so this just graphically sketches out what that means. You've got the slabs running horizontally, and within each slab you have keys that map to values, and this all stands or all sits within memory. Now, normally you don't care about slabs. This isn't what you're worried about. The thing, though, that you do, or the people who care about this are miners. So, and we're miners for the benefit of this talk. Let's talk integration, just to give you an idea again of how Memcache does fit into an application. So we've got a little Ruby script with a hypothetical method there called getUserProfile. And it gets passed in a user ID, and the purpose of this is to connect to the database, pull out user preferences. And so what's specifically of interest here is how Memcache has to be integrated into the application. It's not an automatic caching system. So you can take a Squid proxy, configure it to sit in front of a web application and have it cache automatically for you without the application doing anything. Memcache is a little different. Within Memcache, you have to explicitly code support into your app. And so the first step when we enter this method is to see whether the data is within the cache, and if it is, then we can return early. We exit immediately with the data that we pull back from the cache. If it's not in the cache, then we have to go and pull this from the database. And if we have to go that far, it then gets stored into the cache. So the next time the method gets run, we're going to return early. So it makes it a little more expensive the first time the method's run, but all the following times we should make, or should see quite a big saving. Now those numbers are just for illustrative purposes. They're not at all derived from anywhere. I've made them up. But that kind of gives you an idea of where you would expect to see, or sort of the times that one might see on each of those steps. All right, so by using the cache, we're going to exit out of that early. Okay, and then the last thing with sort of the not the network, with Memcache architecture is that it's quite easy to build them into clusters. So Memcache supports a really simple method for clustering, and that method is that the nodes within the cluster know nothing about each other. It is up to the client to load balance amongst the servers. So the client needs to know about all servers within the cluster, and then the client will pick the server to interact with based on a hash of the key that it's currently dealing with. There's just a few notes there. What that means is that all clients need to know about all servers, and they all need to use the same hashing algorithm. Otherwise, you're going to have quite a mess. Anyway, let's start looking at what Memcache looks like on the network. So it's interesting because by default, it binds to all interfaces on ports 112.111, using both TCP and UDP, right? And that's by default. There are some distributions, some Linux distributions, for example, that'll install Memcache listening on localhost only. But if you pull their source bundle, you get software that binds to all interfaces. Now that's, as an architectural or as a design decision, is questionable. But it arises out of the usage scenario that LiveJournal had, which was they have a really hopefully tightly secured server infrastructure in which they've got competent administrators who know how to keep at least basic network traffic out. So that design decision applies specifically to a usage scenario that is now 8 years old. In addition, Memcached supports two protocols. So there's an ASCII protocol, which is the one that it essentially initially shipped with. And then in 2007, there was an effort to build a binary protocol make it a little quicker than it already was. And so what this means is that to interact with the cache, to set or retrieve values, there are 4 possible code paths. So you can use either TCP or UDP, and on both of those, you can access a binary and an ASCII protocol. And so that's an unnecessarily expanded attack surface, right? There literally are 4 code paths to get to each of these pieces of functionality. And so again, this is another design decision that perhaps made sense when they were thinking about it. But if you're trying to secure it, exposing such a large footprint seems unnecessary. Okay, the ASCII protocol is really simple. That's the grammar for it. There's 18 commands. Top line has got a bunch of commands for storing. The get is obviously for retrieving. There's delete and increment, decrement. The one that's going to be fun for us to play with is the stats command, because that's going to allow us to query info in the cache. And there's a few stats. There's also flush all, which is kind of a nuclear option for removing the contents of a cache, version and a verbosity level, and obviously a quit. So these are pretty basic, right? And I want to show you how easy it is. So we've got a sample cache running locally. So we can connect to the cache, ask it for its version. We can pull some basic stats, for example. Tell us its uptime. Tell us running 64-bit. The number of get commands seen so far, set commands, and so on. We can ask for a few other settings. There's a whole bunch of these that are available. So we can connect to the cache. I can ask it for a key. Let's ask for the key foo. You notice at the bottom I get nothing back. Let's put that at the top. So I get nothing back with foo. We can store foo. Now, when we get foo, we get the contents back, right? So this is what the application does in the background when you're interacting with the cache. It's just speaking this really basic protocol. Now, you can also set expiry times and so on. I'm not going to get into that. I mentioned the slabs, and the slabs become important. So we can ask Memcache to tell us about all the slabs that is currently in use. And what we get back here are a list of the slabs. We see the slab ID sits before that colon. So we've got slab 1, slab 3, and at the bottom, slab 14. So there are many possible slabs that could be in use, but actually we can ask Memcache which ones are actually in use, and it tells us. And the last command, which we'll talk about, is this. It's basically a debug command, stats cache dump. And we can say for slab 3, give us 10 keys from slab 3. And it lists for us the keys. So we've got a key. What do we do with a key? We can simply get a key, and we get the contents of that key. All right. So I will discuss with you the significance of why this becomes fun. Within that protocol, is anything missing? What's missing there? Anyone care to shout? Authentication. Right. There's none, zero, nothing. There's no authentication within Memcached. And again, this is a decision, a design decision that was taken 8 years ago when LiveJournal had a very specific use case that they were trying to build this for. But times have changed, and things have moved on. And so it's not good enough today to assume that Memcached is going to be run by these experienced administrators sitting in tightly controlled networks. I will point out that actually when I say there's no authentication, that only applies to the ASCII protocol. Within the binary protocol, there is support for SASL, but it's not foolproof for reasons I'll get into later. Okay, so as I said, they're pretty clear about this as well. On the website, they'll point out that you shouldn't deploy this, and publicly accessible places, and it shouldn't be on a public network. But it does remind me a little bit of 1999. I mean, no auth on the network, services that listen by default on all interfaces. There seem to be some lessons that are missing here. All right, so I mentioned there's a binary protocol. I'm actually not going to talk too much about it. This is just the packet for the binary protocol. And the reason I've got this slide is these are just the opcodes for all the operations supported by the binary protocol. And the reason I'm documenting it is because it's not available apart from trawling through the source. Okay, so moving on from that, I think it's time to attack. So the first thing that we did was we constructed a fuzzer for that protocol. The grammar, as I said, is really simple. It's 18 commands. And so we fuzzed memcached. So what we found was a denial of service condition. Again, it's one of the code parts, the UDP binary protocol. So there's a pretty easy denial of service where you need to send one packet per thread. That's assigned. By default, there's 4 threads. So you send 4 packets that the UDP channel falls over, pushes utilization on the box up to 100%, which may or may not be an issue. What's nice about that memcached protocol that's specified, that ASCII protocol, is it's been co-opted by a number of other pieces of software. So not just memcached use it. So there's a memcached DB, which is a persistent key value store that's network-based. And a number of other pieces of software expose memcached interfaces in addition to their regular ones, because they're designed to be drop-in replacements for memcached. So the fuzzer was useful in that sense. We wrote it for memcached, could run it against a number of other pieces of software. So with memcached, we can segfault it and assert or trigger asserts. But we didn't follow that any further. It's not really of interest to me. Okay, so given that we understand the protocol, it then became a curious thing for us. Well, can we find these things? And the reason it was of interest to me is when I discussed this with colleagues, one of the reactions was, look, you're not going to find this stuff. Memcached shouldn't be exposed to the internet, blah, blah, blah. And so a bit like that monkey, well, actually, that's quite a smart monkey, I have to say. He's using a spear there to catch a fish. So in fact, that monkey was probably smarter than I was when I started this. It then came down, well, where do we find these memcached servers? Where can we look? And so first effort was blindly scanning randomly. So see if you can pick that up, and we didn't have too much success. Found a few machines, but not that many. And if you're looking to target particular companies, looking for their memcached, it's unlikely that you're going to find them. So there's a whole bunch of variables that have to collide, and it's like saying, well, I'm looking for IS5.printer on that company. Unlikely you'll find it. If you scan the internet, you probably will find it somewhere. But there is a slight difference to that example when it comes to memcached, because if you're looking for these large-scale systems, there's one place they tend to go. They're not going to run their own, unless they're huge, they're not actually going to run their own data centers or their own infrastructure. And what you'll find is that they tend to go towards hosting providers or cloud providers, whatever that means. Right. So how about we look at those in particular, hosting companies or cloud providers? So that's where we're going to try and find this stuff. And then it becomes, well, if we know, or if we've got to guess where to look, the question then becomes, what do we look for? And so it's pretty basic. You're looking for an open port. Now, you can either scan with the TCP or the UDP interface. TCP is going to give you more reliability, but UDP is obviously a lot faster. The question arises, is the set of hosts listening on UDP equal to the set of hosts listening on TCP? No, probably not. But at this point, we're looking for initial targets. We're not looking for, we're not trying to be exhaustive here. So we wrote this little thing called memcache finder, which is a simple UDP scanner for memcached. And so all it does is sends out a version packet and tries to find memcached. Now, actually, this is true. I meant to have network. I don't, so I'm going to skip that. Well, we can run it locally. It's cool. It's cool. I'll run it locally. We're all good. Okay, so we've got this thing, and we can... so I'm just going to scan my local machine. And so it just picks up that there's a memcache listening locally. Because it's UDP, you can do things like scan a /16 or a class B in about 5 minutes, which is enough to at least show whether or not there's likely to be memcache servers in there. And so we did that, and we found a whole bunch. So this is just the /16 that troopers.de sits in. And you'll see there's a bunch of memcaches that are exposed to the net. This is another /16, just showing you how long it takes. So that's 5 minutes to scan, and it picks up a bunch of them. So you just provide it with addresses, and it goes off and does its thing. So you can find caches pretty quickly. So you found the cache. The question is, how do you profit from the cache? And so what would be fun is if you could extract all the contents of that cache and see what data they've got stored in there, and try and determine who's using the cache and what it's being used for. Because it's no good just finding a cache somewhere out on the internet. If there's not interesting data in there, or if you don't know who's using it, then it's a bit like just picking chewing gum off the road. You're not really going to be able to do much with it, right? Okay, and then the last one, which we will talk about, is overwriting entries in the cache. So we scanned a provider. We found 250 caches, which was almost one in every class C that we looked at, which is pretty high density. The question then becomes, well, how do you prioritize? So I've showed you those commands already, the get, the set, and the stats. But the stats is the one that will allow us to prioritize the cache we want to look for. So we've got those. I've already showed you the stats slabs command, and to show you how to get the IDs. I also showed you this cache dump command, which becomes really the core of the tool, which allows you to pull out a number of keys from any given slab within the cache. So there's a few caveats, I guess, when it comes to this command. So it's only going to return 2 megs of key data. But if you're looking at 30 bytes for a key, more or less, you're still getting tens of thousands of keys back, which should be enough to at least find out whether this is an interesting cache to look at. And again, there's a few more caveats there about expired keys and so on. So where does this get it? Well, it means that by connecting to a memcache server, you can get it to provide you with all its keys. And because you get all its keys, you can get all the values of those keys. So you can get its data. So you can mine that cache, right? So if SQL injection is too hard, this is even simpler in terms of complexity. But I think the nice thing to do in a memcache is to think of overwriting data in that cache. So if you consider that the data within the cache is being used by an application that's probably being served to users, then this is a way for attacking users of that website, for example. So embedding malware, whatever the case is, inside the cache, having it being served through a website to its users. But the one that I'll talk right at the end is you can also attack the server side in the application server in specific instances. All right, so we've got this tool called GoDerpa. GoDerpa is this memcache miner, and I'm not going to go through all of its options, but essentially we can pull data out of a cache and write data back into the cache. So let's look at, it's got basically 4 modes. So the first mode is a fingerprint mode. And fingerprint mode will simply connect to the cache and pull out a whole bunch of those statistics we talked about. And that's useful because if you've got 250 caches, you want to know which are the ones which store the most data, which are the ones that really are interacted with very frequently and transfer lots of data. So there's also monitor mode, which I won't demo, which basically repeats the fingerprint but shows you the changes. So you can see if the cache is in active use or not. The second thing, though, the most useful mode is this leech mode. And what leech does is it connects to the cache, and it'll extract as many keys as it can, depending on parameters that you supply. So what we've got here is it's connected to the cache and pulled out 4 keys, and we can look at the values associated with those keys. So if we look at that value, you'll notice that, where are we? Okay, so that's the value of that key. Does anyone recognize that language? Okay, how about, okay, so this is the value of another key in the cache. Anyone recognize this? Okay, it's a Python pickle object, which is nifty. Okay, so what this means is that we've come across a cache, we've extracted data, and we look at the data, and in this particular case, we get lucky. We see there's some kind of HTML. So one way to find the user of the cache is to take some of this and Google it. And we Google that, and we come across this nifty little website, which is the iPad competition page, which is fantastic, because all you have to do is go into the page. It's not actually the iPad competition page, obviously. But for demo purposes, let's go with it. All right, so you need to submit a username and a password here. All right, and so sorry, a username and an email. You submit that, and you get entered into the competition. So we've downloaded the contents of the cache. This is one, I guess, pretty lame way that you can start to make things like cache modification work to your benefit. So we can change the contents of the page in the cache. And I guess we should probably remove the form as well. Okay. So what I've done is I've changed that file, but locally on my machine, right? So it's only sitting on my own machine. I now need to write that back into the cache. So Godurpa supports that as well. And so hopefully now when we connect, so the cache has changed. It's important to note we haven't changed the contents of that page on the server or in the database. That still exists wherever it is. But because it goes to the cache first to generate the page, we can change what the client sees. And for attacking clients, that's all that actually matters. All right, so we've spoken about the leech mode, and I've showed you now the write mode for writing data back into the cache. And so you can also remove data out of the cache if you want. Okay, actually, this is what I meant to do this for the fingerprinting. So when it comes to the fingerprinting, you can pull out all of those statistics that I mentioned, put them in something like a spreadsheet. And what's really fun is you can start to see caches that, for example, sit next to each other in a network and have the same amount of keys, or almost the same amount of keys, or similar amounts of traffic. And what that suggests is that these things are part of clusters, that they sit as memcache clusters. So you can then start to, if you're looking to prioritize your attack, you don't have to go after the entire cluster and pull all its data. Just look at one of those, and you'll figure out whether that data is interesting or not. Okay, so when it comes to finding the front end that uses the cache, we've already mentioned Googling for strings that you find in the data, but otherwise it's what you'd expect. So you can look at DNS associated with that cache address. You can see where it sits on the network or on the internet. And when you look inside the actual cache data, then you're just using your brain at that point. So trying to type URLs that you see, any email addresses, those kinds of things. Then the final one comes where you actually are able to execute code via stuff that you inject into the cache. And in certain circumstances, you can get the application server to tell you who it is. Right, so I mentioned we scanned a few networks out there, and we came across almost 900 caches. sitting on two networks. One of them is quite a big network. But interestingly, we found the most caches in the smaller network, which was a hosting provider. So we pulled about 9 gigs of data from all of those. Excuse me. Amongst those caches, the average uptime was about 64 days. I don't know if there's too much value in that metric, but I thought I'd include it. What I find interesting, though, are just the amount of data that they transport. So, for example, amongst all of the caches, they'd carried almost 9.5 petabytes of data, which is a lot of data. And across all those caches, looking at almost 450 million objects stored inside the cache, in those 900 caches, totaling about 60 terabytes of data. For any individual cache, the highest bandwidth was almost 250 terabytes, with 133 million entries in one cache alone, which is a pretty highly used cache, as you can imagine. And that one stored about 19 gigs worth of cache data. So let's look at the results of some of this. So the things that we find in the cache are quite varied, and that's because Memcache allows you to store all sorts of things in the cache. It just takes a byte stream, essentially. And so HTML and all sort of the things associated with that were in the cache. So JavaScript, lots of data, email, passwords, which we'll look at. So clear text, some of them were encrypted, some of them were really poorly hashed. Compressed data. What was sort of interesting was the types of objects that we did find, so away from just HTML. So serialized objects of a wide variety, so Java, Python, Ruby, .NET, and JSON. SQL strings as well were found in some of the caches. All right, so let's get to the examples here. And there's a few of them. The first one is the site that you probably haven't heard of. It's called GlobWorld. And so these guys are like, they were in beta at the time, sort of a kids game site. And within their cache, we pulled the contents, and they were storing user objects which had the username and the password in the clear inside the cache, and which allowed us to log on to GlobWorld. Trooper Games is a manufacturer or a developer of games for Facebook mostly. So if you've played, and so really a lot of users use their games. So Mafia City Mobsters, I don't know if anyone plays, but if you do, then your data was sort of exposed. And so what they were exposing specifically was Facebook, or the data that Facebook shares with application developers was stored in their cache, so things like your friends list and so on. The next one was GoWalla. GoWalla's a location-based service. I don't know how popular it is in Europe. I think it's a competitor to Foursquare in the US. In other words, you check in at a point and your location gets stored, blah, blah, blah. Do all the social media stuff around that. So within their Memcache server, or within their Memcache, they were storing the passwords. And the passwords were hashed, +1. The passwords were hashed with MD5 and no salt at all, at -2, to leave them on -1. So you can take those and put them through whatever technique you want. So if you've got a rainbow table, or in this case, just Google for some of those hashes. So you get now the username and the password, allow you to log in as this guy, whoever he is. The next set, and I'm not going to, this site name I won't mention, just because the other guys had fixed it. These guys were indicative of, I think, a broader problem. So just very briefly, what you've got there is an email and a password stored in clear text. But it points to a deeper problem, which was using our email addresses as identifiers for ourselves, because people tend not to reuse passwords, or to change passwords. They reuse passwords. So within this particular Memcache, there were a whole bunch of emails and passwords. And what that meant was you just start paging through people's inboxes, Yahoo, Gmail, MSN, Twitter accounts, and so on. And that's because people, as I say, when they use an email address as an identifier, they'll oftentimes use the same password that they use to access that email, which is quite sad, but it happens. Bitly Pro is the big brother of Bitly. Bitly is the URL shortening service. you may be aware of. And so they've got a pro service that adds on a whole bunch of features for analysis and so on your links that you send through them. And so with their Memcache server, they had that exposed, and within their Memcache server, they were exposing API keys and identifiers, so logins in this case. The passwords were hashed, where I couldn't figure out the actual password, but we did have the API keys which allowed you to interact with their API as one of the users. So this is us querying their API as TechCrunch. So TechCrunch is, or was at least, a Bitly Pro user. Second last example is PBS. So if you're from the US, you'll know about PBS. If you're not, it's a public broadcast system, service, I don't know. But basically it's their public TV network. And they've got quite a large site. And in fact, they had a really large cluster of memcaches exposed on the internet. And so what I use this one for is to show that it's possible to really easily overwrite small parts of a web page and have that stuff come out. And taking this notion further of overwriting, this is StockEasy is an Indian website for discussing and tracking activity on stock markets. It's sort of social site and so on. But basically, people here provide recommendations for things, or for things that they think people should do on a website. And this starts to get into the gist of how you could convert simply working with the cache into actually making money. If you pick a user who's got a lot of trust on this site, and you start altering in the cache what this guy apparently says, then you can persuade other people to perform actions. It's a stock trading website. There's a whole bunch of scams that I'm sure you may be more familiar with than I am. But yeah, it's a bad thing. All right. So I want to talk just a little bit about those serialized objects. And in particular, the pickle ones. And I picked pickle specifically. We found lots of pickle. In fact, out of all those serialized objects, pickle was the most common thing we found inside the caches. And pickle, if you're unfamiliar with it, so it's just a Python method for writing objects out to a byte stream of some kind. And it's intentionally insecure, right? So this is the pickle page, and there's a big warning sign there that says, as of Python 2.3, there are no security checks when it comes to pickle. And why pickle's interesting is because when you depickle an object, when you convert it from a byte stream to a Python object, it gets run through a little virtual machine inside the Python runtime. And that virtual machine has the ability to call methods inside of the Python runtime. Right, so you can see that gears starting to turn there. While it may be true that if you pickle something onto your local disk and read it back, pending file system attacks, or putting those aside, that's probably an okay thing to do. But when you write into a cache server somewhere on the internet and it's exposed, then you cannot be sure about that data that's coming back from the pickle. And so this is a published piece of pickle shellcode to execute os.system with the echo hostname parameter. And unfortunately, this was the most that is publicly available for pickle. So kind of for us sparked off a whole discussion of what you can do with pickle, and we've got a paper that's ready to be submitted. It turns out you can go a lot further than just that. There's some issues with that. So let's look at that briefly, because I think it's quite cool. All right, so what I've got here is the Python, is the object that we edited earlier. So let's completely clear it, and let's try that pickle shellcode. So we'll perform a directory listing and write that back into the cache. You'll find okay, we expect that to happen, right? So what's happened is that pickle's been loaded, but the page broke. However, if we look in the logs of, there, okay, so we've got our ls executing. This is in the log file of the server, right? So the command executes, but we don't see output within the web page. And the page breaks. So let's see if we can work on this a little bit. So I'm just going to restore this to where it was. It's a virtual machine. We can start playing with it. It's got a stack. It's kind of got registers that it calls a memo. So by playing a little bit with pickle, we figure out that we can actually get this thing. Let's use a sleep. We figure out some shellcode, right? Rats. Write this back into the cache. Now, what is our expectation here? What we expect to see is the page taking a while to load, and eventually it should load successfully. And so we'll see at the bottom, we're waiting, and if we count to 10, very roughly, after 10 seconds, the page will load, and it shouldn't break. All going well. Right, so the page hasn't broken. This is a good sign. Lastly, well, there's basically 2 more steps. The question then becomes, well, now we can get stuff to execute, but we're not seeing it. Is there any way that we can make this work a little better? And it turns out there is. So we browse the Python libraries. We find there's a subprocess module that will return the contents of the command. So one of the problems with os.system is it doesn't return the contents. We browse there. We can now get code execution by seeing stuff come back. Let's make that even better. Let's pass in parameters. That means it broke. So there's always a bit of fun. I need one more there. Okay, so now I'm getting, I can execute arbitrary commands and get the data back inside the web page and pass in any parameters that I want to the command. Which is a pretty big deal. Like it's, like, thank you for that. No, so when I say it's a pretty big deal, in the sense that we're looking now at systems that have multiple assumptions that are being violated. So Memcached had a whole bunch of assumptions. Pickle had a whole bunch of assumptions. And together, it's kind of made a pretty messy situation. OK, so that's the pickle thing over. We need to move quite quickly. The fixes for all of this stuff is quite simple. Don't expose your Memcache to the internet. It doesn't support authentication at this point in most libraries. So if you run Memcache, it cannot be exposed to anyone except people whom you absolutely trust. Listen on localhost if that's possible. If your libraries support it, convert to SASL. You can disable the code if you want. If you're running a website, protect your passwords properly, for one. Coming just back to this point that I made about the simplification of the dev provisioning process. It can be dismissed, but I think it's quite interesting that when we've got this now example of 2 poorly, well, not poorly designed, but the assumptions that were made when designing these systems haven't stood the test of time. And so 7 or 8 years later, we encounter these kind of these issues. And with making less knowledgeable people responsible for security, you get things like this. I think this was on Rackspace's website. So I hope Andrew Gray's not in the audience. I doubt that he is. But they feature his name quite prominently on the website. And basically what it says is he's sitting in front of the machine and he's just logged in as root on the machine that is just booted up on their cloud service. And he's never used Linux before, and now he's got a working Linux machine and his root. And that's the guy who is now deploying software that's accessible on the internet. And he works for a university. It's likely that the university will come to depend on that service in some way. So there's conflation of roles between, you have an Amazon account, now you can run machines on the internet. It's something that we need to be really, really aware of. Okay, one random thought, this can't be new. I thought it couldn't be new when I first found it, but in almost a year since it's been out, no one's told me that they found it first, so I thought it was kind of weird, given it's so old. There's other ways, I imagine there's other tricks to try and figure out the cache. They're over there. If you put data on the internet, know that it gets stored in places you never thought. Your Facebook data winds up in someone's memcache that's exposed on the internet, I guess. And a couple of places to keep looking. The one thing I'll leave you with is if you thought that Redis was any better, and if you're a big fan of Redis, actually Redis is worse. So Redis supports the explicit retrieval of keys as part of the protocol. All right. I think there's not too much time left. Are there any questions? Like maybe take one, and otherwise we'll discuss at lunch. That will be easy. Cool. Thank you very much.
Okay. Thank you very much, Marco. I think very interesting stuff. We will take 2 or 3 minutes to change the laptops in front before the next talk will start, and give some of the people from the defense tracks the opportunity to change the rooms.